Bismillahirrahmanirrahim. Alright class, welcome to the third lecture of week 2, and I'll start right away. In the last uh, lecture we were discussing Cartesian coordinate system in pretty much detail. We are actually trying to define a coordinate system, and to define a coordinate system we need to define few things about that system, and one of that thing is the definition of fundamental surfaces. And on the basis of fundamental surfaces we define point and the origin. Okay, so the third and most important thing in defining or describing or developing or creating a coordinate system is to define unit vectors. The unit vectors which are primitive to that particular coordinate system. So we ended up, we already discussed each and every points here except the points in this column 7, 8, 9. One thing which I should correct here is that in the last class I mentioned the unit vectors associated with the differential surfaces as ax, ay, and az. You might have guessed that I meant I, j, and k. So actually you should always remember that notation of unit vectors depend on author to author. It varies actually. So many use I, j, k, and you are more familiar with this because you came from the intermediate background in which I, j, k are the unit vectors used for pointing in the direction of x axis, y axis, and z axis respectively. But there is another notation which is used in Nathan Ida, and x cap, y cap, and z cap is another set of notation is another way of noting the set of unit vectors pointing in the direction of x, of y, and of z. William Height used another sort of notation. He used small a subscript x cap, small y subscript y cap, and small a subscript y cap, small a subscript z cap. So unit vectors in the direction of x, y, and z. So we will rarely be using this notation because in electrical engineering we have got specific meaning for I is for current. We have got specific meaning for J. We have specific meaning for K. So just to avoid, since we use I for current, we use J for iota, and K is for wave number, which falls into the domain of optics and wave propagation, and also electromagnetic waves. So we normally don't use I, j, k in electrical engineering. Rather we use x cap, y cap, z cap, or a to the subscript x, and so and so. Alright, so I just used I, j, k in the last lecture, and probably this would be the last time I would use I, j, k. Either I will use this notation or that notation. The cap over each letter will signify that this is actually a unit vector, and I will urge you all not to be lazy while writing a unit vector. Always put a cap on it, okay? Otherwise I won't be able to recognize whether you're talking about a variable x or you're talking about a unit vector in the direction of x. So appending an x, always putting an x is a must for while writing any numerical or any theoretical thing whatsoever. All right, so this discussion we already did in the last class, and I would like to move on. Okay, so all right, so the point number 7 which we have is position vector. Position vector, as the name suggests, is a vector that locates position of an arbitrary point And whenever we talk about position of an arbitrary point, so it means that that position should be defined with respect to the fixed reference point of that particular coordinate system. In our case, we call it origin. So position vector always starts from origin, the tail of that vector is at origin, and the head of that vector is at that point. So that's the reason why we have a specific notation for this. This is almost universal. Everybody use a small r to locate a position vector. Any vector which is starting from any arbitrary point which is not origin and terminating at any arbitrary point which is not origin can be represented by any letter. Normally in this course we will use capital R, okay, but small r is specifically reserved for the vectors which start from origin and pointing in the direction or locating an arbitrary point P. Let's say we have got a point P whose coordinates are x1, 0, 0. So position vector definitely in 3 dimensions. We are using right-handed coordinate system x, y, and z. It means that we have a point on the x-axis. How far from origin? X1 units. So actually, as I told you earlier, that the way of looking at this is that these coordinates are the address. These coordinates collectively is the address of point P, which now needless to repeat, but I am repeating, that is actually the intersection of 3 planes, x equals x1, y equals 0, and z equals 0. And we won't draw these orthogonal planes here, but it is understood that this point lies on the intersection of these 3 planes anyway. So if someone is here and he wants to reach at point P, so we'll say that, okay, move in the direction of x, how many units? X1 units. Okay, here, there we go. So this is the position vector R. So the way to write it in mathematical form is R is nothing but move in the direction of x, how many units? X1 units. So this is how we write it. Alright, so if there is a point which is lying somewhere here, let me represent by a cross, and okay, to reach that point or to give the address of that point or to locate that point, let me call that point Q, and let that point be x1, y1, and 0, meaning that this point is lying on this on the plane which is a horizontal plane at z equals to 0, right? So in other words, it is lying on xy plane. So how to reach that point? To reach this point, okay, just drop perpendicular on x-axis, perpendicular on y-axis, okay. Whenever you drop perpendicular on y-axis, remember that this perpendicular should be parallel to x-axis. Many students do this blunder that they try to just draw a straight line. Remember that this is a 3-dimensional thing which we are trying to draw on this 2 dimensions. So you have to make your drawings and imagination clear. So any line which is along x-axis should be like parallel to x-axis. So why are we dropping these perpendiculars? Just to know that what is the relative position of this point with respect to origin. So actually this point is x1 units in the direction of x with respect to origin, and this vector is, this point is y1 units away in the direction of y as compared to this origin. So we can say that if you want to reach this point, move in the direction of x, x1 units, and move in the direction of y, y1 units, okay. So to do vector addition, you know, we can just slide this vector from here to here, or this vector from here to here. We can say that okay, this vector is also the same as that one, because we are keeping the orientation and just sliding it down a little bit. So to reach this point Q, I would say that move in the direction of x, how many units, x1, and move in the direction of y, how many units, y1, and you will reach this point. Okay, so earlier when we were discussing point P, we had only one component in x direction. Now we have got two components of motion, or two components of movement. So we would say that if you want to reach this point, let me put P here, position vector locating point P, position vector locating point Q will be achieved if you move in the direction of x, how many units, x1 unit, and then you move in the direction of y, how many units, y1 units. So add these two components together. Okay, so add these components together and you will reach at this point. And let's say now we have got another point R, which has got coordinates x1, y1, and z1, and I want you to give me the address of this, the location or the position vector of this point. So it actually the point, the vector which will locate this point will be the vector starting from origin and terminating at this point. Remember that this vector is not on yz plane, it is somewhere in the middle. Okay, let's say I am z axis, my this hand is y axis, my this hand is x axis, so that point is somewhere here. The tip of this marker is point R, and let's say this nose is origin. So any vector that starts from my nose and ends at this marker tip will be the position vector, which will be locating R, and we will represent that position vector as RR. Okay, so how to reach this vector? This point is displaced x1 units in the direction of x with respect to origin, y1 units in the direction of y with respect to origin, and z1 units in the direction of z with respect to origin. Okay, so this point, this is origin and that's the point. So this point is displaced with respect to my nose, how many units in the direction of x, x1 units. This point is displaced with respect to my nose, how many units in the direction of y, y1 units, and how many units this point is displaced with respect to origin, that is my nose, is how many units, z1 units. Okay, so I'm looking in the direction of x1 unit, and the direction of y1 units, and the direction of z1 units. Okay, so I would say to reach this point, just start from origin, move in the direction of x1 units, move in the direction of y1 units, and move in the direction of z1 units. You will reach this point R. Remember that this z1 and this height are obviously the same. So actually if I connect this and this, these two have got the same height, that is z1. So I can say that earlier we had in this case only one component move, and we said move in the by one component we mean move in the direction of x, that's it. In this case, in the case of Q, we had two components. By two components we mean that we were saying move in the direction of x and move in the direction of y, but in this case R we have got three components, meaning we are saying that move in the direction of x, how many units, x1 units, Move in the direction of y. How many units? Y1 units. Move in the direction of z. How many units? Z1 units. Okay. And since each of these terms is a vector, add them together to get the resultant position vector. I think I made myself clear here. So in order to reach a point, we just we can represent that point in a position vector. We use position vector to locate that point, and how we locate it, we just discussed it. So in short, if we don't have this picture, if we had this point and we would be asked to find the position vector, what we would simply do, we will write small r subscript capital R, that is our position vector locating this point capital R. And what we would do, we will just take the x component x1 and multiply it by unit vector ax. Then we would take the second the y component and we will multiply that by unit vector in the direction of y, and simply we will take the third component and multiply that by the unit vector in the direction of z. So this is how we do the position vectors. This is how we locate a position vector. Okay. So in the last class, when we were discussing the diagram, the differential surfaces, the differential volume and differential, meaning this diagram, when we were discussing this and we used a box, a tissue paper box to represent that. So actually what we had a box. Okay, we had the box like this. Again, this is z, x and y, and we said that that point was point P. Coordinates are written over the blackboard over there, and this point which is towards us, right, this which is towards us, and we call that point Q. Okay, so this point, let me just embolden it to give you an idea. Okay, and this point is at the back. Okay, so we said that this width is dx, the depth is dx, and this इसकी चौड़ाई dy है, and the height is dz. Okay, so we said that okay, this P had got the coordinates over there. Let me just write it down: x1, y1, z1, and Q had the coordinates x2, y2 and z2. So we can by knowing the width, height and depth, we can see that x2 is nothing but x1 plus dx, y2 is nothing but y1 plus dy, and z2 is nothing but z1 plus dz. Okay, so any unit vector that starts from this point P and terminates at this point Q, this one, we can call it diagonal vector. Okay, so we said that okay, keep it here. Okay, I want you all to pause here. That we want the unit vector that starts from P and terminates at Q, and we call that not unit vector, a vector, a differential length vector, and we call that vector as dl. Okay, so I would like you to pause here and we'll come back to this later on. Okay, so if we have got a point, let's say a point P, that's a totally different story. Okay, let me give these number a different these points a different name. A, let's say A is 1 comma 2 comma 3, and we have got a point B which is let's say uh, 2 comma 4 comma 7. That's okay. So if we have got this three-dimensional coordinate system here, x, y, and z, okay, point A is 1 unit in the direction of x, 2 units in the direction of y, and 3 units in the direction of z. Let's say roughly the point is here, and we have got point B, 2 units in the direction of x, and 4 units in the direction of y, and 7 units in the direction of z. Okay, let's say roughly that point is point B. So we know that the unit vector which is locating point A is RA, and we can simply write it first thing 1 multiplied by AX plus 2 multiplied by AY unit vector, and 3 multiplied by AZ unit vector, and simply similarly RB unit vector in the direction of which is locating point B is simply AX 2AX plus 4AY plus 7AZ. Okay, so if someone asks you, if I want to give me a unit vector, a vector that locates point B with respect to point A, or the unit vector or the vector, sorry, which starts from A and terminates at B, and let me call this capital R A B. Capital R A B is the vector which starts from A and terminates at point B. Okay, so this is the three-dimensional view which may not be that much appreciable for you all, but let's say I just draw it in a simpler fashion. Let's say we have got this point A, same coordinates, and here we have got point B, and this is origin. Okay, now I'm drawing a totally different thing to just give you the way to calculate this RAB. So let's say this is origin, and origin has got coordinates 0 0 0, we all know that. So the unit vector which will be in the direction of A is RA, and the unit vector which again I'm using the wrong term, not unit vector, the position vector. Okay, and the position vector using pointing in the direction of B is RB, and we have already calculated that. Okay, these coordinates are the same. I'm not changing those coordinates. I'm just giving you a rough picture. 2, 4, and 7. Okay, so if I want to find out a vector that starts from A and terminates at B, then we should realize that actually this is what? This is a vector addition problem where position vector RA plus RAB is equals to RB, head to tail rule. Okay, this vector plus this vector is this vector. So if I want to find RAB, what I need to have is RB minus RA, position vector RB minus position vector RA, and position vector RB is nothing but 2AX plus 4AY plus 7AZ minus AX, RA is AX plus 2AY plus 3AZ. Okay, so the vector that starts from A and terminates at B is nothing but just multiply, just take the difference of respective unit vectors, respective components, sorry. So AX plus 2AY plus 4AZ. So this is the answer. Or in other words, what we have done, we have taken the respective components of B and subtracted that with the respective component or respective point in A. Okay, since the vector head was on B, so we simply subtracted the respective coordinates of B from respective coordinates of A, meaning we subtracted 2 minus 1, which is 1. So here we have got 1, and we just multiplied that by AX. Then 4 minus 2 is 2. So here we have got the answer 2, and we multiplied that by AY. Then 7 minus 3, 4. We put 4 here, and just multiplied that by unit vector AZ. AY plus 4 AZ. This is how we got, right? So if we apply the same method here, we know that Q has got the coordinates x2, y2, z2, P has got the coordinates this. And if we want to find the vector that starts from P and terminates at Q, so what we have to do simply is subtract the corresponding coordinates, and which means x2 minus x1, and then multiply this by the unit vector AX plus y2 minus y1, and multiply that by AY plus z2 minus z1, and multiply that by AZ. Okay, and this expression tells us x2 minus x1 is dx, y2 minus y1 is dy, z2 minus z1 is dz. So we then got this result dx ax plus dy ay plus dz az. This is how we got the formula for differential length. And in order to find its magnitude, meaning this differential length is a vector, so if you want to find the magnitude of this vector, we just take, you all know the magnitude, which is dx square, square of the x component plus square of the y component plus square of the z component. This came from the fundamental vector analysis that you must have seen in your intermediate, or from the fundamental geometry, which you might have seen before. Okay, so that's all for this Cartesian coordinate system. Position vector we have already defined. Now we have got point number 8, which is vector components. So these components, these components are the vector components of the vector RAB. dx-ax, dy-ay, and dz-az are the vector components of the differential length vector dl. Okay, so ax, 2ay, and 3az are the vector components of the position vector Ra. Okay, so now this brings us to another term which is known as scalar components, which you all know of as the projection. Actually, you all know that, so I don't think we should discuss that in detail. So what's the difference between vector components and a scalar component? If this is a vector component, this is a vector component, this is a vector component of RAB, then simply 2 and 4 and 7 are the scalar components in the direction of x, y, and z. Okay, just remove the unit vectors and you will get the scalar components. So That's the thing which you all know very well. Okay, so we have discussed everything here now so far. All right. Final thing is scalar product and vector products. Scalar product or the dot product, you all know. I don't have to, explain it. I just want to tell you one thing. That's why I'm writing it. If you have got two vectors A and B, okay, and you want to take the dot product of that, okay, let's say A is written as this. Ax, Ax, Ay is in terms of its rectangular components, and if we have got another vector B who can be written in its vector form, in vector component form, like this. Okay, so if you want to find the scalar product or the dot product, because the answer is a scalar of the dot product, that's why we call it scalar product. What we can do is we can multiply the magnitude of A, magnitude of B, and the cos of angle between these two. Okay, so let's say this is vector A, this is vector B, and this is theta. So we just use this. We all know how to find the magnitude of A and magnitude of B. Magnitude of A is nothing but ax square plus ay square plus az square whole under root. Similarly for B. Okay, but how about this theta? This theta is it's difficult to find. It's difficult to find theta in 2 dimensions. It can be found, but in 3 dimensions it is way too difficult to find. If your vector A is here in this direction, okay, and B is in this direction, how can you find it? If A and B are coplanar like the one drawn here on this board, then it might be simpler. But if they are not coplanar, A is pointing in that direction and B is pointing in that direction, how would you find this theta or the angle between A and B? So for that we have got, you all know that, as a formula in which we can simply use these vector components to find the dot product. And another more easy formula in which you don't have to find theta is just multiply the respective rectangular components, and then you will get the dot product. Okay, so one of the most important applications of dot product is to find projection, both scalar and vector projection. Okay, let's say if I've got a vector A here, and if I've got a vector B here, okay, and here we have got some angles. So if I want to find the scalar, if I want to find the scalar projection, I just have to drop a perpendicular here. By projection we mean that let's say, suppose someone is throwing a light directly over from the head of A, vector A, and which is the direction of that light is perpendicular to B. Okay, directly over A, but the direction of light is perpendicular to B. So the projection जो उसका साया बनेगा वेक्टर A का B के ऊपर, that projection will be of 90 degrees with respect to the direction of vector B. So this distance from this point to this point is nothing but what? Is nothing but scalar projection. So how we find the scalar projection? How can we find the scalar projection? We can find scalar projection by finding a unit vector in the direction of v, okay, and then just take a dotted with b, okay. So a dotted with b means a dotted with the direction of b means magnitude of a, magnitude of b, which is magnitude of ab unit vector in the direction of b, which is 1, and cos of the angle between the two. So actually we have got the formula, since this is the right angle triangle, so we got the formula for calculating the length of the base, which is in terms of vector quantities. Vector algebra is a dot unit vector in the direction of b. So this is what, this is scalar component, because it will end up in a scalar quantity, that is the length of the projection. If I just multiply this by the unit vector AB again, I'll get the vector component, okay, vector component, but this time the multiplication is simple multiplication. It is not dot. It cannot be dot, because you cannot take dot between a scalar quantity and a vector quantity. Anything which the operation which is given in parenthesis will end up in a scalar quantity, so you have got only one option to multiply it scalarly, okay. So as you all know that if we have got vector a and we have got a scalar number n, so if I just multiply n by a, then the resultant is the vector which is in the same direction but is now n times the size of original vector a. If n is greater than 1, then this resultant will be larger vector in the same direction as the original vector a, and if n is smaller than 1, then it will be a smaller vector. Similarly, division works in the same way. Division of a vector by a scalar quantity works in the same way, okay. So I just wanted to repeat this because you will need this thing in your end of chapter problems a lot. That's why I just had to repeat that. And you will also see the term scalar components and vector component. The scalar component is nothing but the psi, nothing but the projection, and vector component is nothing but psi multiplied by the unit vector, or the scalar component multiplied by the unit vector. That's it. Or the projection multiplied by the unit vector. The third thing and the last for this discussion of Cartesian coordinate system, that would be a cross product, and cross product is also known as vector product, because the answer is always a vector quantity. Oh, I just mistakenly remove this. Let's say we have got two vectors given in terms of its their two vectors represented in terms of their vector components, and we want to find the cross product, okay. So we all know that magnitude of a into magnitude of b into sine of theta from a to b. Now since we are using sine, so the direction is also important, okay. If you're okay, so because sine cos of minus theta is cos theta, but sine of minus theta is not sine theta, it is minus sine theta. So now subscripts are important, and since we have got we should have the answer as a vector quantity, so we have to multiply this scalar thing, magnitude, and this is also a scalar, by unit vector. And we all know that from our intermediate physics that if you have got two vectors A and B, okay, and we have got an angle between these two, so cross product will give us a vector which is perpendicular to the plane on which these two vectors are present. Okay, so for this example, this whiteboard is the plane. Let's say I have drawn the coplanar vectors where they are sharing this plane of the whiteboard. In that case, the resultant of the cross product will be a vector in the direction of this marker, either going out of the board or going into the board. Okay, so direction is given by direction of the result is given by the right hand rule. If we are taking A cross B, okay, if you are taking A cross B, meaning we are moving from A to B, in that case thumb wheel is going into the board, so the resultant is going into the board, and the magnitude of that resultant is given by this. And if we have got B cross A, so in that case we'll have to measure, the angle in that direction and curl your finger from B to A, then thumb will show you the direction of the resultant vector. So magnitude is always the same, the only thing that differs is the direction, and that direction is totally out of phase, 180 degree out of phase. So we can say that A cross B is nothing but negative of B cross A. And there is a bunch of applications for cross product. You might have remember from your intermediate physics, and I'm not going to discuss that. You can use these vector products, vector products or scalar product to find area of a triangle and whatnot. Okay, so similarly, as was the case in a scalar product, it is always difficult to find this angle between A and B. So let's say again, if this vector A is in that direction and vector B is in that direction, it is really difficult to find the angle between these two vectors. Okay, so what we have, we also have a formula for that, in which we don't have to find the angle between these two, and you are all aware of that formula, which is normally given in this form. You can use the vector components, just put those vector components in this matrix form and solve this matrix, and you'll get the answer. You don't have to find the angle that is theta AB or theta BA, whatever it may be, depending on the case, whether it is A cross B or B cross A. Okay, so that's it for today. And inshallah from next week we'll try to start cylindrical coordinate system and spherical coordinate system. And now as I said before, I won't give you any formal assignments, but remember that I would expect you all to open your books. Either you open the William Hyde book or the book which I shared with you on the Google platform, thanks to the publishers who provided that to us. And try to solve all those problems which are related to Cartesian coordinate system, which are related to vector addition, subtraction, dot product and cross product before, remember that before upcoming live session. I expect you all that you must have completed that. uh, this subject requires a lot of practice. One of the few reasons for which this course is considered very difficult uh, is that most students do not give too much time on this, because I said that this is a very demanding subject. I wrote it in the Google Classroom as well. This is a very demanding subject. You have to take charge of it. It cannot be spoon fed to you. I have, I am trying my level best to deliver whatever I can here, just the way you would if we were, not having these online classes. We were having actual classes. I'm trying to give the same environment, and now I would expect you all to take responsibility as well and open your books and start solving those problems. It will demand a lot out of you to understand this course. So practice. This is what I would say. Just go through the lectures, go through the textbook, see the solved problems, see the drill problems, see the end of chapter problems, try to solve them all. If not all, at least try to solve the odd number problems. And when you are comfortable with odd number problems, because normally the answers to those odd number problems are given already in the book, so when you feel comfortable, then you can just go and solve the even problems. So this is what this is the best piece of advice that I can give you. You don't have time, to solve the problems or numericals in this class. Remember that the paper is 90% numerical, and unfortunately we don't have time to discuss those numericals or solve those numericals in the class. So it is your responsibility. I'm explicitly mentioning it. It's your responsibility. If you want to score higher in exams, in midterm, and in any other sort of assessment, you must take responsibility. You must open books. You must consider that this is your course and you have to pass it, because at the end of the day, the marks which will be awarded to you are going to be shown on your mark sheet or your transcript. You cannot you won't be able to say, and that's for any course. You cannot say that my marks are not good in this subject because so and so problem was happening, or I could not understand the course, or teacher gave us the too much work. I told you before, this course is a lot demanding, but it will change the way you think electrical engineering, and it will definitely change the way in which you see the world, inshallah. The world of physics and science. Okay, with this, see you in the next week, inshallah. Assalamu alaikum.